For Part A of the study desk problem, we're asked to determine the expected on-hand inventory of desks to maintain a 97% in-stock probability. The first step of this, we'll have to find the optimal order up to level to achieve that in-stock probability. In order to do this, we're going to use the formula S is equal to the mean plus Z times the standard deviation, where our mean and standard deviation are over L plus 1 periods. So let's start out by calculating the appropriate Z value. We know that we're looking for an in-stock probability of 97%. So when we look this up in the standard normal distribution function table, we see that corresponds to a Z value between 1.88 and 1.89. Using the roundup rule, therefore, we're going to decide to use the Z value of 1.89. Now let's calculate the mean over the L plus 1 periods. That's equal to N, our new N, which is our lead time is 2 weeks, so 2 plus 1 is 3, times our mean demand in the shorter period, which is 100. Therefore, we had a demand over the L plus 1 periods of 300. For standard deviation, we're looking for the square root of the L plus 1, so square root of 3 times our weekly standard deviation of 65, and we get a standard deviation equal to 112.58. Now plugging those values into that original formula, we get 300 plus 1.89 times 112.58, and that's equal to 513. Next, we need to calculate the expected back order. Expected back orders are equal to the standard deviation times the L of Z. We know our Z value is 1.89, and looking that up in the standard normal loss table, we see that that corresponds to a value of 0.0113. If we multiply that times our standard deviation over the L plus 1 periods of 112.58, we get expected back orders of 1.27 desks. Now, we know that expected on-hand inventory is equal to S minus the expected demand over L plus 1 periods plus the expected back orders. So therefore, we know that's equal to 513 minus our expected demand over the L plus 1, which we saw to be 300, plus expected back orders of 1.27. And we get an expected on-hand inventory for each desk equal to 214. But now, since we know that we have two desks that have the same mean and standard deviation, we know that the expected on-hand inventory for both desks is 2 times 214, or 428. For Part B, given that we now think we might be able to pool the stock for the base of the desks, it asks us what is the expected on-hand inventory of black tops. Here, expected on-hand inventory is still 214 units because the demand distribution, the lead time, and the target in stock is the same as before we came up with this new ordering strategy. So the answer to Part B is equal to 214. Finally, for Part C, how much less inventory would be required? Again, the answer here is 0. The order up to level of the gray bases has to be the sum of the order up to levels of the tops. If it were lower, then there's a chance that demand is less than the order up to level of each top, but more than the order up to level of the gray base, in which case the in-stock probability would fall below 97%. Hence, to ensure that the in-stock probability remains 97%, there must be one gray base for each top. If the in-stock probability on the tops were raised, then the number of gray bases could be reduced and still achieve a 97% in-stock probability. For that reason, again, the answer to Part C is 0.